Okay, hello everyone. Welcome to another seminar in computer engineering. Hola, Eduard, ¿qué tal?
Hola, bien, ¿y tú?
I'm practicing my Spanish. And today we have a topic, byEduard, that I don't like in my projects. It's security. Man, security is always complicated. And it's great having you here today. Eduard works at Telefonica. I was visiting Telefonica last summer, and actually, Fabrizio, one of my talented PhD students, is one of the team members of Eduard's team at Telefonica. And I convinced Eduard that he should be in my seminar classes and present a little bit, bring this topic that it's not that I don't like it. It's complicated security, and that's precisely what Eduard is going to talk about. As usually, Eduard, I don't read your biographies. There are, and you always you keep it small, but folks can find more about you over Google Scholar, LinkedIn, and contact you. And the idea, folks, for those of you watching live, as usual, is that you prepare your questions. You can leave them over the YouTube chat channel. And in 40 minutes, more or less, Eduard, let's talk about the topic of your talk. And you can try now your screen sharing.
Yes.
And I will be looking whether our students have done their homework as usual, and pick up some questions.
Okay, I think
I can see your screen, and probably you go now in full mode. Okay, great. Okay. Thank you.
So thanks a lot, first of all, Christian, for the nice invitation. I mean, it's very good that you invited me, but you didn't have to convince me. I was very happy to do it from the very first moment that you asked me if I wanted to participate in this seminar. It's good that now I get to see what the other side of this is. I mean, I've been following these seminars on the other side as attendee, and today I'll be happy to talk to you about the security of confidential computing. Basically, first, I will give you some introduction on what confidential computing is, what are the real security guarantees that confidential computing offers, and then I'll go and I'll present a paper that we published last year in Euro S&P, which is one of the top security conferences. Okay, so let me start a little bit about myself. So my name is Eduard. I'm Spanish. I studied Asians in Spain in UPC. Then I did an Erasmus in Belgium. I joined the COSI group, which where basically I started doing cryptography. I also continued with my interest in networks. And I ended up doing a PhD on wireless security. Then after my PhD, I became very interested in this software-defined networks, network function virtualization, and I did a visit in the University of Padua for 6 months. After that, I did like a 1.5, 2-year postdoc in the University of Birmingham, where I looked at the security of hardware security anchors and trusted execution environments. One of the topics of today is one example of such a hardware security anchor. And then during COVID, I joined Telefonica. I joined as a research scientist. And then, last year, I was given the responsibility of leading a small team of researchers, basically working on network and cloud security. Okay. Let me talk a little bit about the areas of expertise of our team. So basically, we intersection between the privacy and systems. And our goal as a team is to understand, perform, detect, and mitigate advanced security attacks. Okay, and we do this. I always like to say that we do this through a combination of offensive and defensive research. Okay, and as of now, we have 2 main lines of work. One that I like to call next generation networking, which is basically very related to how networks have evolved in recent years towards being more software-defined and more programmable than before. There I left a few keywords that may resonate for some of you. We've been looking at SDN, network function virtualization. Currently, we have quite a lot of works that explore programmable data planes. So basically, this ability of running certain computations in programmable switches and smart NICs. Quite a lot of ability through BPF, among others, RDMA and others. And then we also have this line of research on cloud computing security, where basically we've been looking at new application development models, basically move away from this traditional way of implementing applications, as everything together inside a virtual machine. No, this is not a good thing anymore. Now we're going more towards building solutions that are more modular. So for example, we've been looking at microservices, we've been looking at serverless computing more recently. This is on the way these applications are developed. Of course, these applications also need to be running somewhere, right? And we all know virtual machines, but we know that these virtual machines are very slow, and very heavy weight. So some new sandboxes have been proposed, from Docker containers that many of us know, to more like secure containers like gvisor proposed by Google. There are also some proposals on more lightweight VMs, so VMs where we strip some functionalities and we keep only what is needed. More recently, we've also started looking at WebAssembly as a quite promising sandbox that offers very good security and performance. And then we also have this line of research on confidential computing. What is confidential computing? Suppose that you want to execute some application in the machine of someone that you don't like. Okay, it could be a cloud provider, it could be a friend that you don't like. Of course, this person has root privileges in this machine, and the question is, how can you execute your application there securely? Meaning, without your friend or without this cloud provider learning any of the data that you're using, because it could be the case that some of this data is sensitive. And we also want to avoid that this honest cloud friend learns the logic of application, right? We think that some of these applications may contain IP, and we want to hide this IP from others. Okay, and today I propose to, let's say, solve this problem or look into, let's say, investigating how to solve this problem through trusted execution environments. So what is confidential computing more from the beginning? No, so let me give you some context on this. Traditional cloud computing usually has followed this model that is relatively weak, because usually when we think about security, we think about protecting these customers' applications at rest and in transit, but not while in usage. Okay, so I think that most, if not all, security experts would now recognize we're protecting a relatively well understood problem. It's not easy, but I think that now we would agree that it's a let's say problem that we know how to solve, but I've never thought relatively recently how to protect this while it's being used, while it's being at runtime. Okay, what happens? What happens here is that even if we have data, we have the code of our application encrypted at rest, at some point we need to decrypt it because we need to use it, right? Before our CPU can run this application, we need to see exactly what we want to run. And at this point, it needs to be decrypted. It's at this time that this application, this data, is in clear text. And any privileged type of software in our machine, or anyone who has physical or administrative access in that server, could see the data and the code, or could even tamper with that. Okay, it could make changes to this. So this is quite problematic, and this is the reason why confidential computing exists. Okay, what are trusted execution environments? I always like to think about a trusted execution environment as a sort of like box where I can move all the sensitive data that I don't want anyone else to see. I can also execute arbitrary computations inside that. And this box is a bit like an isolated context that no one else can see. Okay, and it's a very strong concept if you think about it, because it allows protecting against extremely powerful things who even have root privileges in the server. Okay, so we are creating a box. We can form applications, we can store data without, this being exposed to someone who has this is really, really strong. And this security comes, say, from two main type of protection. So this isolation comes from the hardware, and there are different, let's say, underlying primitives, hardware-based, that help providing such strong security guarantees. And there's also this concept of attestation. No, I mean, okay, now we have this box. In this box, we place all our computations. But you could ask yourself, okay, how do I know? I mean, suppose that I'm a customer and I want to run my application in a specific cloud provider, but I really want to know that this cloud provider is running my application inside one of these isolated boxes, right? Inside one of these TEs. Do I know this? Attestation is the mechanism that you can use, graphic guarantees, that your application has not been with, and that your application is now running inside one of these protected areas. Okay, and so far we've seen two main, let's say, T's flavor. Okay, so at first the idea was a little bit like, okay, let's create small security memory areas, what I would call enclaves. And let's try to secure these very small memory areas. Okay, so basically, I mean, at first there were some constraints on how much code and data you could store there. Okay, and then this was the philosophy behind Intel SGX. Intel SGX appeared in 2015, more or less, and the security community picked a lot of interest on this. I mean, this caught the attention of the security researchers, and Intel SGX was attacked in quite a lot of different ways from the community. And then, I mean, at some point, people started thinking, okay, it's hard to protect those very small enclaves, no? And this sort of led to what came next, which was, okay, what if instead of creating these very small secure memory areas, what if we try to protect entire VMs? And this is what AMD tries to do with his approach. Okay. And now you would say, okay, is this something new? Is this being adopted? Who has been working on this? Why should we care about this? It's something that many important vendors are currently using and are currently working on. Since already a few years, what we're seeing is that there's a lot of industry-wide conversions towards hardware-baked security. Okay, so we want our security to be baked in the hardware itself, and there has been quite a lot of effort into let's say achieving this vision of or realizing the concepts around confidential computing. Okay, so we began with Trust Zone, which was proposed in 2004, which basically was type of TE primarily for mobile devices. Then Intel introduced SGX in 2015, bringing TEs to mainstream CPUs. And then this was followed by others. So AMD, SEV, which is an extension of the previous one. Then Intel with TDX also started moving from this, like protecting these very small security memory areas to protecting entire VMs with TDX. And something also that I find quite interesting is, okay, now we have quite a few examples that show that we can have these secure compartments in CPUs, but what about GPUs, right? I mean, we know that these days GPUs are used quite intensively. We know that when training these models that are trained on GPUs, protecting, like offering this extra security in the GPUs themselves, no? And NVIDIA has been looking into this. So NVIDIA is now looking into how to offer these confidential computing guarantees also in the GPUs, which is super interesting. Let me go a little bit more in depth on this. So going a little bit back, what is the problem here? No, so the problem is that in traditional systems before this, there was this layered design. No, so basically we have the hardware with the TPM, CPU, memory. Then usually we have a hypervisor. Then on top of this we have a OS kernel. Basically, each layer is trusted by the layer above. No? But here the problem is that there are too many things that are green. No? So in security, we like to talk about the trusted computing base, no? Which basically it's a concept that we use to denote all the components that need to be secure, that cannot be compromised for the security that we want to achieve to hold. Okay, so in this case, basically this application that is malicious in red cannot compromise any other application if everything that is in green remains green, right? But what we've learned over the last decade is that something that we want to achieve or something that we want to move forward is going into a trusted computing base that is as combination of components that weaknesses, that there are no bugs. It's really, really hard. No? So usually when designing a security system, we try to identify this trusted computing base, and we try to go for, we always have this mentality of trying to minimize the trusted computing base as much as possible. Okay. So take home message here, the trusted computing base was huge. What is the goal of TEs? The goal of TEs is to reduce this trusted computing base. So now with the TE, even if the OS kernel, the hypervisor have been compromised, we still have a guarantee that this for many attacks is safe up. Okay. And now is this, we still need some components in the bottom layers to be trustworthy, obviously. But as you saw, the reduction in the TCV is significant. Okay, which is very interesting, and it's the way to go. Okay. Now, how does this apply in the cloud? No, so in the cloud, basically what we typically have is containers. Usually, these containers, if you deploy a container in the standard way, there is no confidential computing, so you need to make, let's say, additional requests. This container to be protected under the security guarantees that confidential computing. Usually, kind that containers share the same OS, and that attacks can come from different ways. No, so it could be that there's a confidential container where there's an adversary that tries to escape and tries to compromise the kernel. So here, I want to leave it up to your imagination to imagine all the security attacks and all the security problems that can happen in a multi-tenant shared infrastructure. Okay, and something that I want to highlight as well is that these confidential computing concepts in the cloud are very widely used. Okay, so major cloud providers, AWS, Google, they have all incorporated confidential computing products into their portfolio. Okay, so this is very widespread, and I also want to say that this kind of technology is not only in the cloud, happening in high-end servers, but even our mobile phones, our laptops have such many of them have this kind of capability. Okay. Of course, as with any technology, especially those that are proposed for enhancing security, it's not perfect, right? It's a very complicated type of problem, right? Recall that what we're trying to achieve is to create a secure environment in a machine of someone that we don't trust, right? This is extremely complex. And basically what has happened is that since SDX was proposed, as I was saying before, a lot of security researchers have been investigating on possible ways how to attack this. Okay, and even before going to the different attacks, what I want to say is that this is a very standard process. So what we like to do as security researchers is to attack, okay? And ultimately, these attacks don't need to be seen as the technology that we're attacking is weak, but they need to be seen as the technology is so interesting that everyone wants to get their hands on this and wants to propose attacks. And ultimately, all this process is very positive because only by exposing the technology, only when you're sure that lots of security experts have looked into this, and of course the corresponding countermeasures have been applied, only then you can start to be sure that this technology is strong from a security point of view. Okay, but going to the attacks, what we've seen that these things can be attacked from different angles. No, so there are these so-called microarchitectural side channel attacks, where basically the tries to deliberately an observability of low-level events. Okay, and for example, in this kind of scenario, there are certain shared components, and these caches can be exploited. So you have, suppose that you have a server where you have multiple confidential containers. Ultimately, they're all using the same caches, right? Because they are running on top of the same server. And basically, what we've seen is that these shared components can be exploited for attacks. No, and there are variants. I put here some names. I don't want to go much into the detail of this, but there are many different types of examples that show how a malicious confidential container could infer information about another server. There are also these transient or speculative execution attacks that are an extremely interesting line of research. No, just to give you a little bit more context, we know that in the clouds, in data centers, performance is crucial. We always want to run things faster, and we're always thinking about ways to optimize things in the CPUs. CPUs these days include a lot of optimizations to try to give you this next level performance improvement, right? And one such, let's say, optimization, and it's something very, very strong, is that these days CPUs are trying to speculatively execute your code, which basically means even before the CPU knows if a specific instruction will be used, the CPU will already execute to have the result of this computation in case it is used. Okay, what happens? If in the end this is not needed, this is thrown away, right? So this is never exposed in the usual way. But these computations that happen, regardless of whether they are in the or not, they leave a trace in these shared components. So for example, there are some effects on the cache itself. Okay, and this is basically what these kind of attacks try to exploit. Then there are controlled channel page fault side channels. Okay, where basically the goal is to try to inject faults. See, for example, try to measure how long it takes for one instruction inside this confidential container to run, right? So basically, attacks where you have a lot of control on low level, these low level events that what is happening. And then one last class of attacks is what I called physical and software-based fault injection attacks. No, so recall that the threat model behind this is that I can run applications securely in a machine that I don't control. The adversary, of course, can have full control of this. No, it can have not only root access on the machine, but it also has physical access on it. No, what that means is that STEs should offer protection against someone that has physical access and can open and start also trying to leverage this kind of physical access to, for example, tap information or introduce information on a bus, right? And there are attacks that exploit this. So there are attacks that try to introduce these glitches, these faults, directly on the physical interfaces. And there are also some others that try to do this in software by leveraging some capabilities that servers. This is interesting. Well, there's this example which there's a plunder bolt in which the authors are trying to exploit the fact that CPUs can change the voltage frequency dynamically based on the workload. Okay, so what the goal of this paper was to try to introduce. So they were trying to undervolt the machine where the confidential container is running, to try to induce faults by undervolting the machine. Okay, and it's interesting because in our case, the paper that we're also trying to use this, let's say, case not to induce any faults or not to induce any glitches, but to infer information about the confidential containers. Okay. So up to here, what I presented is different classes of attacks, and I would say that as a summary, to me, the main takeaway message is these attacks, despite, it may seem that there are a lot, and because there are even more than those that I showed in the slide, these attacks have ultimately resulted in improving the security of these TEs. Okay, sometimes at the cost of decreased performance, because some of the mitigations that were proposed came at the cost of compromised performance, which is not ideal. But ultimately, the security of TEs has improved significantly because of all these findings. Okay, and we were thinking, okay, this is a relatively well understood field, and of course, there's still a lot of work to be done. But we were also interested in, okay, there are some registers in our servers that also provide quite a lot of information about device usage, right? So this is something that caught our attention, and we wanted to go a little bit farther on this. So let me now move to the paper, now that you hopefully understand better what confidential computing is. So as I said, this paper is online, is available online. If you read it and you have some questions, I'll be super happy to answer them after my talk, or you can also reach to me via email. Okay, so this is work that we presented at Euro S&P last year. Let me also, go back a little bit and try to motivate the reason why we published this paper. No? So as I was saying before, modern CPUs now have these capabilities to dynamically adjust their voltage and frequency in response to the workloads. So basically, when you go for lunch and your machine is not doing anything, it can run with minimum voltage frequency. And of course, when you're running some computationally intensive type of operation, you're training children, this voltage frequency has to, you're increasing this value. Okay. Of course, the goal of such mechanisms is to achieve an optimal balance between CPU utilization and power consumption. Okay. So some aspects that I find quite interesting myself. These features are very widespread these days. So they are supported, available on all Linux and Android devices. And then from a security point of view, some aspects that also call quite a lot my attention. They are accessible from user space. They report values with a very, a granularity of 10 milliseconds, which basically means that, lots of changes can happen very, very quickly, and lots of information is being leaked in this way, okay? And then something that I also find quite interesting is that this kind of mechanism provide you this value for every core of your server, okay? This has been used already in previous work. For example, the last one that I mentioned here, this was used to infer which website was being accessed by a user, and it was even successfully used to infer which keys on. Basically, our hypothesis with this work is that this voltage frequency can constitute a unique application fingerprint of, by application, I mean this application that is running inside this confidential container, okay? Let me try to motivate a little bit why we care about this, no? Because it seems to me that this is more of a privacy type of problem, no? So basically, the way we think about this is, I mean, suppose that you have some confidential containers, each running its own application. Under the guarantees of TEs, adversaries should know nothing about these applications, right? So adversaries should not even know which application is running, should not know which version of the application is running. They should know nothing about them. Okay, so this is the promise behind TEs, behind confidential computing. Okay, what we want to see is we want to exploit this voltage frequency information to try to infer which application is running inside this confidential container, and to even go one step further and to try to infer which version of the application is running. Okay, the motivation is, in the first case, if you have no of the application that is being run there, you need to perform. I mean, if you want to perform an attack, you need to perform it blindly, right? I mean, you can try things. If you're lucky, perhaps you succeed, but it's a blind attack. Chances are that it's not very easy for you to successfully compromise the confidential container, and it will probably take quite a lot of effort. No? We're going more into, okay, what if we can use this kind of leakage, right? Because if we can infer which kind of application is being used through this voltage frequency information, clearly there's a leakage. So our point is, can we leverage this leakage to perform more efficient, more effective, and more stealthy attacks? So, like making less noise, being able to create an attack that is more tailored for the specific application that is running inside the confidential container. And here I put an example. No? So if through this, the adversary could infer that what is running inside the confidential computing container is a MariaDB, right? And I mean, suppose that the adversary can even infer which version of the MariaDB is. You could go to one of these vulnerability databases. You could search for MariaDB, and then you would realize that there are some CVEs that basically show some vulnerabilities against this specific version of the MariaDB, right? So then the adversary could say, okay, now I can try to see if this attack, as explained in this CVE, can be used to exploit this confidential container. Okay, so that's the motivation. Threat models. Let me also go a little bit broader, because what we did not only applies to TEs, but also applies to other contexts. And here, basically, what I want to present you is different threat models, different types of attacks. What these threat models have in common is that usually what we assume is that there's a trust boundary. No? So there are different areas, and there's a trust boundary. Okay, so if you're in different trust boundaries, what it means is that you should not be able to learn anything about what is in the other trust boundary. Okay, so what we consider here is a native environment, just a Docker container running in your machine, and the adversary is a user space application, right? I mean, suppose that, I don't know, any application that you can think of that runs in user space that is malicious. Okay, could be a browser, it could be anything that you can think of. And the goal of this type of attack is, can this user level adversary infer any information about the running inside this confidential this container? Sorry. Then we also looked into other types of sandboxes, starting from gvisor, which is a secure type of container, and Firecracker. And here the idea is the same. We have a user space type of adversary. In one case, the application is running inside a container created by gvisor. In the other case, the application is running inside a container that at the same time is wrapped into a micro VM. Okay, the goal is the same. The goal is, an adversary that doesn't have any visibility, that cannot infer anything that doesn't know anything about this application. Could this adversary, through the voltage frequency information, infer which application is running inside this container, inside this micro VM? Okay, and then we have the case of the TEs. Okay, in the case of the TEs is also similar in one way. What we're also assuming, following the standard TE adversary model, what we're also assuming is that the adversary can also be someone that has compromised someone that has access to privileged software. Okay, so it could even be that you launch the attack from a compromised OS. Okay, the goal is the same. The goal is to always try to see you can sort of bypass this trust boundary, and you can about this application. Okay. What else? Okay. So I listed here three main challenges. One, I would say, related more to the collection of the data. One related more to the sort of ML part, I would say. How do you distinguish these frequency voltage signatures? And the other one is to really how to exploit this in practice. No. So let me start from the beginning. So now we have an adversary. The adversary is assumed to be collocated. So the adversary is assumed to be in the same machine as the victim. And the adversary can now collect voltage frequency information about the victim, okay, while the victim is executing. Of course, something that comes to mind is, okay, we first need to find a way to disentangle the voltage frequency changes as a result of the underlying execution environment from the ones coming from the container image itself, right? When doing the work, we also saw that containers, they are not isolated, right? So even if we run containers in different cores, we are not, let's say, limiting, or we're not restricting the activity of the core. So other tasks that are being simultaneously executed in the CPU, they could run in the same core where the container is running. Okay. Then there are also quite a few challenges when this container. One of the challenges is that containers are made of layers, and it's very common for containers to reuse, to share layers. Okay, so of course, the more layers are shared between two containers, the less, the more similar they will be, right? And you can also expect that this will also translate into frequency signatures that are also very similar to each other. Okay? So this was an important challenge. We also saw that when running these containers, there are some containers that are relatively simple, right? So they run for a bit, but then maybe there's a point where they're waiting for a request to continue. So we saw that there are low activity, this is how I call them, low activity type of containers that make make this challenge even more of a challenge. But we also saw that there are some with quite a lot of activity. Okay. Then when it comes to how to really exploit this in practice, what you can think of is that, okay, in practice, of course, we always assume that the adversary is collocated with the victim. So adversary and victim are always in the same server. This is an assumption that we make. But of course, these servers in clouds have lots of different cores, no? And the adversary doesn't know where the confidential container or the container of the victim will run, right? So there may for the adversary to be able to monitor these cores and to be able to, get a hint that the sandbox environment is being created, because when we create this sandbox is an indicator that the container will be executed next, right? So it would be good if we could have a specific pattern or something that could tell us that a specific type of sandbox is being created. Okay, and then also something that we wanted to consider in our work is, okay, in security, when an attack, usually what we want to do is to show that powerful attacks even executed successfully. Okay, what if we limit the adversary to only to monitor this frequency information for a very short period of time? So we thought that, if the adversary had to collect frequency measurements for a very long time, this would probably mean that the attack is not something to worry about, or is not something that we should be worried about now, or that it would have less chances to be exploited in practice. Okay. So what was the methodology that we followed? We divide the attack into two main phases. Okay. So we have an offline phase that happens before it's a sort of like profiling phase. Okay, that happens before the attacker is with the victim in the same machine. So in this offline phase, what the adversary does is, first it wants to create a database, like a data set, of container images, right? So we're trying to fingerprint applications. Okay, we need to know which applications the victim can potentially execute. So first, we need to create a data set, and this data set can be created in lots of different ways. As an example, there are public repositories from which you can get many examples of applications that can run inside containers. So what we did was we built a crawler, we collected information from Docker Hub, and we collected a variety of different images performing different type of functionalities. Then the next step is to configure the specific runtime. So in some cases, it's just Docker. In some cases, it's the secure container from Google, gvisor, or Firecracker, which is a micro VM from Microsoft, or the specific trusted execution environments that we consider. Okay. Here, something that I would like to highlight is that the TEs that are being used by each cloud provider, this is new information. This is public. Okay, so what I'm trying to say is that best replicate the same environment that they will find in reality when they execute these attacks in the cloud. Okay, and then basically as a third step in the offline phase is now we need to run each of these container images separately, one at a time, while simultaneously collecting this voltage frequency information. Okay, so then we collected many samples for each of the containers, and the goal was let's see if we can train a machine learning model that later on allows us to uniquely identify which container image is from a sample. Okay, so then this is something that we did once, and then the scenario in the online phase is now the adversary is really executing the attack against a real victim. As I said before, adversary and victim are assumed to be collocated in the same server. Of course, adversary is this voltage frequency information while the victim is running his containers, can collect a sample, and then can feed this sample into the machine learning model previously trained. Okay, so now the sort of challenge for the adversary is collect a sample, take the sample, feed the sample into the model, and the model, if we do this properly and this side channel leaks enough information, the model should be able to tell to which container image this sample belongs to. Results. Well, just as a small spoiler, what we saw is that the attack works. We tested the attack. As you can see in the table, we tested the attack in different execution environments, not only TEs. Okay, the TEs that we tested are Marin, which is Ventilators DX, and ASCV. There you can see that the attack also in different microarchitectures. Okay, so something that we say in the paper, and I want to highlight, is that we were very interested in portability, but portability understood as the attack is successful across different execution environments and different microarchitectures. Of course, each time we need to train a different ML model for each pair of execution environment and microarchitecture. Okay, so portability, is not meant to with the model and reuse it across execution environments and microarchitectures. So a deep ML model is trained each time. We saw that the average across over different microarchitectures and execution environments is more than 70%. Even more when we consider top 3, top 5 guesses. Sometimes, knowing that it's, even if you reduce the set to 3 guesses or 5 guesses, this can already be good enough for the attacker, because this reduces quite a lot the number of ways that you can attack this confidential container later on. And something that we really liked and to emphasize that the time in the online is extremely short. In it, we can perform the attack successfully with the accuracy in the. Okay. We were also very interested in let's collect for for a quite long time. I mean, 40 seconds for us is a long time. And then we were interested in understanding where, I mean, at point accuracy does not increase or does not increase. And we started to realize that even with much shorter times, we would also achieve a very, very, very high accuracy as well. Okay, so let me move a little bit further. Let's start to go a little bit more on, okay, I really want to prove to you that the attack is feasible in practice, okay? So quick reminder, this DVFS type of functionality in the servers can report these frequency voltage measurements for each core separately, okay? Which means that adversaries can track multiple users or containers at the same time, okay? So we were interested in the FEEC experiment. So I mean, suppose that you have multiple containers being executed simultaneously in the same server, okay? And be careful, because here we're assuming that each container is pinned to a specific core, okay? So each container has its own core. The hyperthreading case, I will come to this later, okay? What we see is that, so here in the x-axis, you see the number of containers that are running in parallel cores. And we were surprised by the result, because what we saw is, okay, it seems that what is happening in other cores is also affecting slightly the ability to fingerprint these containers, right? So what we saw is that on average, every container that we are sort of considering reduces more or less 1.5% the accuracy of our attack, but our attack remains highly effective, right? Even more than the top 3 and top 5 guesses. And then we were also interested in pushing this even further, no? And we started thinking, okay, let's try to see what would happen if instead of pinning these containers in different cores, we let containers run in the same core. No? So we were interested in, okay, I mean, suppose that now we have two sibling threads in the same core, and then yes, then things started more complicated. We saw that really the attack stops working as expected. You have multiple containers running on the same core. The chances that the attack succeeds decrease considerably. Yeah, I mean, by 48.6%. Following with our evaluation, we started trying to measure the effects of assigning containers to multiple cores. So now we sort of relax. I mean, something that we like to do is we start with some more rigid conditions, and then we try to relax of these assumptions that we're making. So before we were making containers were pinned in a core, each of them. Now let's assume we relax this assumption. Containers can run in multiple. Is that as we, so for example, the accuracy running in 2 cores, and it's interesting to see in the top is how the like when it runs on a single core, super clean, right? You can see the periods in which voltage goes. When running in 2 cores, you see that the pattern somewhat, I mean, you can still see the pattern, but you can also see that it's much more noisy than before, right? And you can also see that now execution time has reduced pretty much like half of it, which makes sense, because now you have 2 cores working for the same task. No? But what we saw is that the accuracy also drops there. Okay, so when considering 2 cores, accuracy to 70%, a little bit more. The fingerprinting time reduces, right? And something that's, because we really spent quite a lot of time on this experiment to try to find the best way of doing this. Then, I mean, at first we thought, okay, why don't we take these different samples that we're getting, so in the middle and the bottom image, and we find a way to, let's say, combine it together and then use this combined pattern to create our ML model. Then we realized that this was not working. And then what we started doing was to treat each of these samples for the different cores separately, and to say, okay, this belongs to this image, this belongs to this image, so we sort of label it in the same way. And then we started seeing that this was a better approach. And then moving forward, we also, in the end, we also decided to, because I mean, ultimately this is a signal and it's a very noisy signal. So we started also thinking about different strategies more related to signal processing. So we ended up using some filters, and we did this signal processing, and this is how we reached the result, because really this was not an easy experiment.
Eduard.
Yes.
We are running almost out of time, my friend. Okay.
Almost done. Two more slides.
Okay.
Then hopefully this is an effective side channel, and a very effective way of fingerprinting this application side is confidential on these containers. But then we were also wondering, okay, if we have different versions of the same image, right? Could we uniquely identify each of these versions? And this is a very good example that shows exactly what is happening across different versions. No? So in the first row, what you can see is same container, but then starting from the left, it's one version. In the middle is another version. In the right-hand side, you can see another version. So going from 3.0 to 4.0 to latest. And this is measurement one. So this is the first time that we measured these signatures or these patterns. And then we sort of repeated this once more, right? And you can see that there's very little intra-container difference, right? So patterns between the same container are extremely similar. Are patterns between different versions of the same container are the inter-container version similarity is high. So we started looking into this. So what we decided was, okay, let's run a very small type of experiment to show this. We took 25 images. We took 5 different versions for each image, and we showed that we could achieve an accuracy of slightly over 80%. In terms of countermeasures, we looked into different types of countermeasures, going from, let's say, simpler, easy to implement, but perhaps not super robust, to a little bit more elaborated, but maybe a little bit harder to implement in practice. So of course, what probably would come to mind to many of you is, okay, why don't you restrict user level type of applications from being able to access this kind of information, right? I mean, why user level applications should be able to access this voltage frequency information? Well, this is a fair point, and this could partially solve the problem. But we also see that, for example, in the TE threat model, the adversary is someone who has root privileges, right? So even if you restrict to the ability of user level adversaries to access this kind of information, root level type of adversaries could still access information. Then we started thinking about, okay, what if we inject noise? And we started making a lot of, we started running a lot of experiments on how best to introduce this noise. In the end, what we showed is we found some operations that where we saw that the voltage would increase massively, okay, if we run these operations. And the idea was, okay, while the victim is running his containers, in parallel, we could be performing these floating point operations that are super complex and that require the machine to work at the maximum, like peak voltage, okay? And then we consider 2 scenarios. One scenario where the adversary doesn't know about the existence of this countermeasure. And basically, we saw that the success rate in this case drops significantly, okay? And we also wanted to consider a case where the adversary could know that we are implementing this kind of solution. And then we saw that in this case, the success rate still is at 50%, okay? We also measured performance. We saw that performance is, I would say, relatively decent. I mean, compared with all the level of the making. And finally, we also to read voltage frequency values, perform an operation because you want to read these values every 10 milliseconds. So we thought, okay, this would probably leave a trace when it comes to syscalls that are used. So we identified which syscalls are used for this. And we then wanted to see the uniqueness of this sequence of 4 syscalls that we identified. So we took lots of different applications, we ran them, and we saw that none of them, while it executes, creates this kind of pattern. Okay, so basically what this means is that if the cloud provider, if we want to develop a solution based on this, what it means is that if we identify this kind of pattern, we could have strong guarantees that this pattern comes from an attacker that is trying to get this kind of information. Okay, so I'm now going to the conclusions. Hopefully, I that confidential computing is a very cool technology. It has evolved a lot. It has been attacked significantly, which is good. And I want to emphasize this. What I try to show you today is yet another example of an attack vector that needs to be considered, because privacy is also very important. And when an application is run inside a confidential container, adversaries should not be able to learn any information about this. And we show that this doesn't hold here, right? So basically what I wanted to show is this fingerprinting attack is effective in native, so in only with Docker, in different sandboxes, different types of TEs. The success rate is more than 70% in all environments. But it's to show that the attack is feasible in practice. And then we oppose these countermeasures. And I would say that for more information, I would refer you to the paper. And now I'll be super happy to take any questions you may have.
Thank you, Eduard. I was worried about the time because, as you know, we have the students that now at 2 p.m. Brazil time, they need to join other classes. But let's extend our conversation a little bit. I cannot miss the opportunity of having you here. So if students are leaving, okay, don't worry of our meet link. This is because they have potentially other duties. We have our audience over YouTube that may be watching later offline, who knows. So that's where we should keep at least 10 minutes. And I was checking out here the questions of the students, and some of them they prepared. So they looked what was your abstract. They identified relevant sources, and what they noticed were a couple of them questioning, not focusing in cloud environment, but other trusted computer environments that have less resources. Whether do you see that these threats and these trusted execution environments, how do you see them to apply to smaller footprinted devices with less resources? Is this a trend? Or is this another dimension? How do you see these resource constrained edge devices and the problem space that you have discussed? Of course, it's not necessarily a shared cloud domain, but I would like to know your opinion on this.
Yeah. So what I explained today, fits perfectly also in this kind of situation. Some of the TEs that I mentioned in one of my slides are also being used in, let's say, lower end type of devices. Okay, so ARM, for example, is a company that has focused more on TEs for mobile devices. Okay, whereas, for example, Intel SGX is more high end type of servers usually, even though in Intel processors in our machines we also have TEs. Okay. Edge devices, it's a, what is the edge, right? What is an edge? I also know that I think that some people have been looking at software-based type of TEs. Problem is that this doesn't really work. Okay, the security from these trusted execution environments needs to come from hardware. So you need to have hardware support for this.
you have killed 1/3 of the questions for the students. Like the 1/3 are around, and I will share the spreadsheet with you. I was not sharing right now, but just as a snapshot. But I will share the full spreadsheet. I usually do this in these seminars, where you can see how the students did their homework, selecting related work, and many of them pointed to software. Like, is it really impossible that there is a software solution, or is a software solution really out of the game, or maybe something new in the software space? So no chance.
I don't have any faith that the problem can be solved in software. So at least.
It's good. It's good for the electrical engineers. They have still their opportunity. Okay. Let me ask. What is next? What would you do next? After this paper, because your presentation was really focused on a paper, what would you recommend to an incoming PhD student that would like to follow up? This is one classical question that maybe you have some thoughts that could motivate someone to enter this research space that, as you mentioned, is still long-standing or with many open challenges.
Yeah, I mean, I think that in this kind of research, there are two main lines. No, if you're on the attack side, and remember when I was in Birmingham, we had the paper accepted on, let's say, finding against types of TE, and this is still a very interesting area. I mean, now there are newer TEs, no, these TEs that are trying to protect entire VMs, and I think that at first, some people thought that some of the attacks that were possible against these smaller TEs would not be possible here. And basically now what we're seeing is that even some tools that were proposed for this to attack the smaller type of TEs have now been sort of proposed also to attack these TEs that protect entire VMs. No? So I mean, I think that there's still a very active community on finding attacks. And in fact, we're also working currently now on another in the line I proposed today. Okay, so
oh, great.
Even outside, yeah.
Good. And with that, and you were lucky due to the time, because the next question would be on the artificial intelligence that everyone loves. And there is always one connection of AI. And I would ask you, what would be the role of AI in that security domain? But we will skip this. We'll skip this for today, and I will point everyone to our next week's seminar that touches again networking, wireless networking, machine learning. Okay, and after that there may be a November seminar. I'm still waiting for a confirmation, and if not, then our season will be over, and only in 2026 that we'll be back with another seminar season. Thanks, Eduard, and looking forward to meet you soon in person.
Yeah, it was a pleasure. Thanks.
Thanks. Thank you, everyone. Bye-bye.
Bye-bye.